So let's recap some of the ways that we've developed to show whether or not a polynomial with integer coefficients is irreducible over the rationals. The overarching idea in all of these statements is due to Gauss. It's enough to show that your polynomial is irreducible over the integers, and then it'll follow that it's also irreducible over the rationals. So the first check is to see if your polynomial is degree 2 or 3. If it's degree 2 or 3 and reducible, then it's got to reduce and have a one linear term. If it has a linear term, then it will have a root. So, checking for irreducibility in this case reduces to the situation of checking if you have a root. Now, if you're in the field Z mod P and you're looking for a root, all you do is plug in the different values of x that you have in your field and check if any of them give you 0. If you're over the rationals or the integers, you have the rational root theorem. If you happen to have a monic polynomial, so if the leading coefficient is 1, then you'd have a root that is a divisor of the last coefficient a0. So you could just check all divisors of the last coefficient and see if any of them are roots. If you do have a root, f is reducible. If you don't have a root, it's irreducible. The next statement we've proved is Eisenstein's criterion. That says that if you have a prime p and the coefficients of your polynomial have the right relationship with p, then your polynomial is irreducible. We'll do an example of that in a minute. And the third statement I wrote down here, I didn't prove in a video, but it's one of the exercises in the homework. It says that if you take all your coefficients mod p, p again a prime, and you get irreducible over zp, then your polynomial is also irreducible over the rationals. So let's see some examples. Here's an example. How about we look at x cubed minus 4x plus 1. So this is a degree 3 polynomial. I'm going to look for a root. I'm going to use the rational root theorem because I have a monic polynomial. The only possible values that divide 1 that are integers are plus and minus 1. So we check x equals plus or minus 1. You plug it in here. Neither one evaluate to 0. So I have no roots. That means it's irreducible over the rationals. Okay, let's do another example. What about 3x to the 5th plus 2x cubed plus 6x plus 6? This problem, I think I'm going to use Eisenstein's criterion. I get to pick a prime p as long as the leading coefficient doesn't vanish and the other coefficients are divisible by p, then I'm fine. So what I'm saying here is I'm going to take the prime p equaling 2. 3 is not divisible by 2, but every other coefficient is divisible by 2, and 6 is not divisible by 4. So I need all of these to be even. I need this one to be odd, and I need this to not be divisible by 4. There, I'm done. That's all there is to it. This is irreducible over Q. Let's finish this video with a final example. How about if I look at 2x cubed plus 9x squared plus x plus 5? Well, for this one, I'm going to use statement 3 here. I'm going to take p equals 3. all these coefficients evaluated mod 3 give, so taking mod 3, we get 2x cubed. This goes to 0, plus x, and then 5 mod 3 is 2. Here's my new polynomial, and I'm working in Z3. I could plug in 0, 1, and 2. This is a degree 3 polynomial, so I'm up here in case 1a. I could plug in 0, and I don't get 0. I can plug in 1, and I don't get 0. And I could plug in 2, and I don't get 0 mod 3. So this is irreducible over Z3 and therefore Q.